Good evening, my dear students. Some students demanded video lecture on the design of helical spray. Now let me illustrate design of helical spring with an application problem. I think this problem we have solved in the class was just for the benefit of those students who could not attend that particular class. So I am doing that problem again. Design a valve spring for an automobile engine. When the valve is closed, the spring produces a force of F minimum, that is F minimum is 45 newtons. 45 Newton. Maximum load F maximum is 55 newtons. Then the spring must fit over a valve bush. So please note there is a valve bush here, on that the spring must fit. Okay. So the diameter of the valve bush is given here, the 20 millimeter, that is 20 millimeter. So the spring must fit over the valve bush. At the same time, the spring must sit on the valve seat. So the outside diameter of the valve seat is also there, that is 35 millimeter. What do you mean by this? It means the inside diameter of the spring should not be less than 20 millimeter. What is inside diameter? D minus D should be greater than 20 millimeter, and outside diameter D plus D less than 35 millimeter. So that is the condition. So I have to satisfy these two conditions because the manufacturer has specified these two conditions. So we must design the spring, okay, to the manufacturer's specification. So according to the manufacturer, the inside diameter should be more than 20 millimeter and the outside diameter should be less than 35 millimeter. In other words, the spring must fit over a valve bush of outside diameter 20 millimeter. At the same time, it must fit or it must go inside a space of 35 millimeter. Okay. Now, next, the lift of the valve is given. Lift is given here. Lift is I think 6 millimeter. How much? Yes, 6 millimeter. So lift is 6 millimeter. Spring index is given in this problem, 12. Now some problem the spring index will not be given. In such problems we have to assume suitably spring index. Okay. So by trial and error method we have to arrive at a suitable value of spring index. It all depends on the problem. Of course, in this particular problem, spring it is given. The allowable stress may be taken as tau allowable is given here directly 0.33 GPa. 0.33 GPa is also equal to 0.330 MPa. Correct? 0.33 GPa into 10 raised to 3. So 0.33 GPa into 10 raised to 3, that is 330 MPa. Okay. Now, modulus of rigidity is given. That is 80 GPa. 80 GPa means 80 into 10 raised to 3 MPa. Newton per mm square. Megapascal is also equal to Newton per mm. We all know that. Okay. So, now we have to design the spring. Okay, let me start. No, in this particular problem, allowable shear stress is given. That is 0.33 GPa. In some other problem, the allowable shear stress will not be given. In such problems, we have to select suitable material or the material will be given. So, you have to refer to the table number 11.8 in the data handbook. You go to the table, you find out the property of that particular material. So, that is heat stress, elastic limit, shear stress. Okay. So, shear stress, what is that? Heat stress in shear, heat stress in shear. So, we have to find out that heat stress in shear, that is referred to torsional property. Because we are designing helical spring, we must refer to torsional property. So, we have to find out the stress at elastic limit. Then we have to select some convenient factors, suitable factor safety. Then we have to divide that the stress at elastic limit tau I by the factor safety. We will get the allowable shear stress. Of course, such problems already we have done. So, I don't want to go in detail into all those things here in this video. So, just in case if it is not given, we have to select suitable material from the table and find out the relevant property and then find out the allowable shear stress. Okay, now let us start. And one very important assumptions we will make here in this particular problem, we will design the spring for maximum loading condition. Well, there are different types of application problems. In some problems, we will design the spring for variable loading condition or cyclic loading. So, we have to use some other method. We have to use what is called as the Walsh-Line method. It is similar to our Soderberg-Line method. So, we have to use Walsh-Line method. Then we have to design the spring. Now, of course, in this particular problem, because nothing is given there in the problem, so it is not mentioned. We have to use Walsh-Line method, something like that. So, let us say that let us design for maximum loading condition. So, design the spring for maximum loading condition. Maximum loading condition. What is the maximum loading condition? That is F is equal to F max is equal to 55 Newton. 55 Newton. Now, for safe design, we all know that for safe design, maximum shear stress tau should be less than or equal to tau allowable. What is the maximum shear stress? 8F Ck by pi d square should be less than or equal to tau level. Please note, these formulas are available in the data handbook. Don't mug up all the formulas. Don't mug up any formula. All the formulas are available in the data handbook because God has given data handbook. So you refer to the data handbook. All these formulas are available in the data handbook. 8 Ck by pi d square. What is K there? Walls factor. How to find out the wall factor? 4C minus 1 by 4C minus 4 plus 0.615 by C. What is the spring index here? 12. So for that, what is the value of K? So spring index C is 12. C is equal to 12 here. So let us find out K here. I think if I find out K, that will be 1.119. We will get K. Then you know maximum. F is equal to F maximum. You know that K we know. We C we know. We'll solve for D. Solve for D. When I solve for D, I will get around 2.38, around 2.38 centimeter. Sorry, not 2.7. Sorry, 2.38 millimeter. Sorry, 2.387 millimeter. Now the standard wire size is 2.5 millimeter. I think I have taught you in the class how to find out the standard wire diameter. Now you please refer to the data handbook. There is vast spring wire. You go to that vast spring wire. You please see the increment. So because normally the diameter will be given in terms of increment in steps of 0.5 millimeter or something like that, 0.2 millimeter. So you can please refer to that data handbook. You find out the standard diameter. Now already we know this, how to find out the standard wire size. Now you have to refer to the data handbook and find out the standard wire size. So this is standard. So from some table 11.3 or something. I don't remember the table number. So anyhow, we'll find out that. Now once I find out wire diameter, then mean coil diameter, capital D. Capital D, mean coil diameter. You know that helix diameter, it's also called as mean coil diameter. What is D? C into D. What is C? Spring index, D by D. What is D here? Mean coil dia. Mean coil dia. What is small d? Wire dia. Wire diameter. So we'll find out this. D, C into D, we'll get 30 millimeter. Now let us find out outside diameter, D plus D here, outside dia. This is outside dia, outside dia. This is inside dia. Inside dia, outside dia. Let us find out outside dia here. How much is that? 30 plus 2.5, that is 32.5 millimeter. So I am getting outside diameter is equal to 32.5 millimeter. 32.5 millimeter is less than 35 millimeter. You please here. What is the condition? The outside diameter should be less than 35 millimeter. I am getting outside diameter is equal to 32.5 millimeter, which is less than 35 millimeter. What about inside diameter? D minus T inside diameter. 30 minus 2.5. If I do that, 27.5 millimeter, which is greater than. What is inside diameter? Inside diameter D minus D should be greater than 20 millimeter. So that's also greater than 20 millimeter. It means that both the conditions are satisfied. So we have satisfied both the conditions. Conditions are satisfied. Conditions are satisfied. We have satisfied the condition. Okay. So next, after this, what is that I have to do? We have to find out the deflection. Because the deflection is not given in this problem. So let us find out the deflection. How to find out the deflection? For that, first let us find out the spring stiffness. So let me find out the spring stiffness. Now how to find out the spring stiffness? What is F naught here? F naught is equal to F max minus F minimum divided by Y max minus Y minimum. What is Y max minus Y minimum? That is lift of the valve. Lift, that is given here. Lift is given 6 millimeter. F max we know. Sorry, F max we know. F minimum we know. To solve for F naught. Let us solve for F naught. When I solve for F naught, I think I will get F naught is equal to. Where is that F naught? Not solved here. Anyway, he has done different method. No problem. We can do that. F naught, I am getting 1.667, something 1.67 Newton per millimeter. So the spring stiffness F naught is 1.67 millimeter. Sorry, Newton per millimeter. And what is also F naught is equal to F max by Y max. Now you please, that is the speciality of spring stiffness. You see, the spring stiffness will remain constant. It is also called a spring constant, irrespective of the load, whether it is minimum load or maximum load or any load within that load range, your spring stiffness will remain same. So spring stiffness F naught is also equal to F max by Y max is also equal to F minimum by Y minimum. We can write any way. Any form we can write spring stiffness. So that is the speciality of spring stiffness. Already I know spring stiffness. I want to find out what is Y max. What is Y max? F max by F naught. So when I do that, I think I am getting around 33 millimeter. So 33 millimeter maximum deflection. I think that he has found already somewhere here. Yes, 33 millimeter. Yes, we'll get 33 millimeter. Please do this. Now, you please do the calculations later. You please cross-check whether it is okay or not. So, Y max is known. Now, once I know Y max, the next thing is that we have to find out the number of coils. So, knowing that Y max, now let me find out the number of coils here. Now, let us find out the number of coils. So, find out the number of coils. How to find out that? We know that Y is equal to Y max is equal to 8F C cubed I by GD. I know wire diameter, I know modulus of GD, that is G, already given. How much is that? 80 into 10 raised to 3 Newton per mm square. This is known. C is known. Number C, 12. And wire dia, 2.5 millimeter. All other things are known. F is equal to F max. That's also known. 55 Newton. Everything is known. Y max is known. Y max. Y is equal to how much? 33 millimeter. All are known. Solve for I. Solve for number of active coils. Solve for number of active coils. Active coils, I is equal to, we solve for number of active coils, I think I is equal to, we'll get, 1 minute, I will get 8 point something, 8.6, 8.7 I am getting, because I can't adopt 8.7 coils. No, we can't have 8.7 coil. Either it should be a 8 coil or it should be 9 coil. No, preferably on the higher side, let us take it as 9 coils. 9 coils. Next, assume square and ground end. Now, please note all these formulas are there in the data handbook. I am not writing any equation number here because I am not referring any data handbook here. Now, please refer to the data handbook. You please check these formulas. Assume square and ground end. Assume square and ground end. So, if I assume square and ground end, solid length, let us find out solid length. LS, solid length LS is equal to I plus 2 into T. We will solve for solid length. Similarly, let us find out free length. What is free length? Free length is equal to LF, L0. Free length L0 is solid length LS plus maximum deflection plus we have to give some clearance. We know that clearance I have to give. So free length means when the spring is not loaded. What is solid length? When the spring is fully compressed. So if you want to find out the free length, first I will find out the solid length. For that I will add the maximum deflection plus to avoid that the contact stress, excessive contact stress, we must have some clearance between each coil. Now how many clearance I have to give, how many gap I have to give, I minus 1 gap I have to give. Each gap is 1 millimeter. If I solve for L0, I think you please solve for solid length. I don't know exactly here. Solid length, I think he has not done that. So anyhow, no problem, you please calculate this, that is 9 plus 2 into 2.5, all those things. Now please do these calculations, please. So millimeter, I will get free length, and then pitch. I'm going to find out pitch. What is pitch? L0 minus 2D by I. You solve for pitch, I think approximately pitch will be around 7 millimeter. Approximately, I am not sure about this. And free length will be around 70 millimeter, approximately. Okay, now I got pitch. So finally, I have to check for buckling. So check for buckling. Check for buckling. Buckling failure. Check for buckling failure. Buckling. So if I want to avoid buckling failure, the free length should be greater than 4 times the mean coil diameter. Now let us check whether free length is greater than mean coil 4 times the mean coil diameter. The free length is around 70 millimeter, approximately 70. 4 times the mean coil diameter. Now what was the mean coil diameter? I think 30 millimeter. 4 into 30 is 120. So, but free length is not greater than 4D. Because free length is around 70 millimeter. Because in this case I am getting 70 millimeter. So since L0 is equal to 70 millimeter less than 4D equal to 4 into 30, that is 120 millimeter, there is buckling failure. There is buckling failure. Okay. So if I want to avoid buckling failure, you have to find out the critical load. Or in other words, what is the critical load that will cause buckling failure? Now you please find out this critical load also. F0 into L0 into KL. What is KL there? Load factor. Load factor. Now you please refer to some table number is there. You find out the load factor. It depends on the L0 by D ratio. L0 by D ratio. It depends on L0 by D ratio like this. 2, 4, something like that. So you just find out that. So for square and grounded. For square and grounded. For square and grounded or built-in end. We call it as built-in end. Both are same. Built-in end. You find out KL here. You please find out approximately find out KL. So then once you find out KL, you just substitute here, find out critical load in Newton. So that is the procedure. So this will give me complete design of helical spring. You can tackle any type of problem. If you understand the procedure of one problem, design of helical spring, one problem, you can design any problem. Is it okay? I hope you understood the design of helical spring. Thank you.